Hello, everybody. Welcome back to more Econ Talk. It's a very exciting day today. We're going to look at a new type of graph and one that you've probably heard about just colloquially on the news and that sort of thing. We're going to be looking at demand curves. So the types of graphs we have been looking at so far have been graphs where the two axes represent the amount of two different goods that you consume. So a point on this graph, the x-coordinate represents how much of good x you've consumed, and the y-coordinate represents how much of good y you consumed. We are going to start looking at demand functions. For demand functions, the horizontal axis is still the amount of good x you have are consuming, but the y-axis is going to be the price of x. So we're going to be able to look at this and be able to answer questions like, oh, if Diet Coke costs $2, this is how many Diet Cokes I'm going to demand. If the price of Diet Coke goes up to $10, this is how much Diet Coke I would consume. So price is going to be on the y-axis and quantity is going to be on the x-axis. Real quick note about demand functions in economics and later on supply functions. A lot of times we are going to be writing demand functions like this. The quantity demanded is equal to 10 minus 0.5 times the price of x. The price variable is going to be on the right-hand side of the equation. Normally in math, that means that variable would be on the horizontal axis. In economics, we don't do it that way. It's a long centuries-old convention about how graphs are drawn in economics. So even though we're going to be writing equations that have price as appearing to be the independent variable, we are always going to be putting price on the vertical axis. It's kind of a pain because if I ask you to actually graph this demand function, the first thing you have to do is solve this for p so that you can graph it the way that you know how to do. You'd have to do qx minus 10 equals negative 0.5 px. Then divide everything through by negative 1/2. So you get negative 2q plus 20. And then you're in a form that you all are comfortable graphing. So just something to keep an eye on. We'll bring it up every once in a while. You're not going to have to actually graph anything in this presentation, but just keep it in mind. Okay, so how do we generate a demand function starting from the graphs that we're familiar with? So here we have on this graph the indifference curves and budget constraints for two goods, Diet Coke and video games. We start at point A, the red line, so that's originally Diet Coke cost $50 per unit. And my income's $100, so at that price point, I can only afford 2 units of Diet Coke, so that's why we have a very steep budget constraint. And when I find the optimal bundle, I find that I actually end up consuming only 1 case of Diet Coke. So that means that if I were to make a little table about price and quantity of Diet Coke consumed, when the price of Diet Coke is 50, I only consume 1 Diet Coke. And then we can say, okay, well, what happens if the price of Diet Coke goes down to $12.50? So that's where the blue budget constraint is. The price of Diet Coke went down, so now the slope of budget constraint changes. At that price, my new optimal bundle is here. I consumed 4 units of Diet Coke, so in my little chart, if the price is $12.50, I consume 4 Diet Cokes. And then let's say the price of Diet Coke goes down to $5. That's what the green lines are. The price of Diet Coke drops even more. When the price of Diet Coke is $4, I'm going to consume 10 units. So, sorry, $5. So, we could keep changing the price of Diet Coke and drawing the new budget constraint and finding the new optimal bundle and recording how much Diet Coke I could get. And I could generate as many points as I want to, as many pairs of price and quantity that I want to. And that would generate the demand curve. Because remember, on a demand function, it's price on the y-axis and quantity on the horizontal axis. So, I'm just finding points that are on the demand function here by changing the price of Diet Coke. And on the next slide, we actually have that graph. So point A was 1,50. That was the first point I found in... this is the first point I found when Diet Coke is really expensive and I'm only consuming one unit. Here's the second point we found, B, where the price of Diet Coke was like $12.50. And here's the third point we found when Diet Coke was only only $5. I'm consuming 10 units. So if we kept changing the price of Diet Coke over and over again, we would trace out this function. So this presentation is only about how to derive demand curves graphically. We'll look at how to do it algebraically in the next presentation. So you would end up getting a demand curve that looks like this. Okay, so notice that when we were going through this process to derive the demand function, the only thing we were changing was the price of Diet Coke. This is like incredibly important. We've been doing a bunch of shifts around with indifference curves on the type of graph we've looked at. We've considered changes like what happens if your income goes up? How would that affect your optimal bundle? What happens if the price of good X changes? How would that affect your optimal bundle? What happens if the price of good Y changes? How would that affect your optimal bundle? Yada, yada, yada. In this process that we did in this presentation to get the demand curve, we did not change your income or the price of other goods. The only thing we changed was the price of Diet Coke. And that is incredibly important. Demand curves only, the way we derive demand curves assumes that other things that might affect how much you're going to consume, like income and the price of other goods, so in this situation, the price of video games, those are not changing. Those are constant. So along this demand curve that we've drawn here, the price of Diet Coke is changing. That's what's pictured on this graph. But your income and the price of video games is constant. So along a single demand function, everything else is held the same. So income is held the same. The price of other goods is held the same. The only thing that's changing is the price of good X. In this case, Diet Coke. When we change only one thing at a time, and hold everything else equal, this is called the all else equal rule. And there's a Latin phrase for it that's very popular in economics that you'll hear a lot. Ceteris paribus, for you Latin scholars, I know that's not how you actually pronounce it in Latin. However, that is how every economist in the world pronounces it. Ceteris paribus translates into all else equal. So a lot of times you will hear things like, if the price of Diet Coke goes up, how does that affect your consumption of it? Ceteris paribus. That just means everything else that's not the price is still held the same. So all else equal, what happens to your consumption? So you'll probably need to recognize this phrase. It comes up in the textbook and any kind of economics research writing. So eventually we're going to look at what happens to a demand curve when you change the price of another good or your income changes and that sort of thing. But when we are deriving a demand curve, we are assuming that everything else is being held equal. So that's it. There's an explanation on here, some pages in the textbook where the explanations for these concepts are. So you can take a look at that if you want. If you have any questions, bring them to class, and I will talk to you later.
With a dream, my cardigan. Welcome to the land of fame excess. Am I gonna fit in? Jumped in the cab, here I am for the first time. Look to my right and I see the Hollywood sign. This